Hey guys, Buildzoid here from Actually Hardcore Overclocking, and today we're going to answer the one great question. Does the Maximus XI Hero have a 4-phase or an 8-phase? And the answer is, I guess you'll have to... Good spot to put the ad break here, Steve.
Before that, this video is brought to you by Nzxt's new H500 case, which we recently found to have an impressively effective cooling setup that is entirely negative pressure when stock. The H500 is the successor of the S340 and S340 Elite, offering high build quality that's all steel and glass, and cable management features that are also top class for this $70 compact mid-tower case. The H500 is a part of Nzxt's new H-series lineup, which also features options for mini ITX, micro ATX, and full ATX builds. Learn more at the link in the description below.
Anyway, the answer is it's a 4. No, seriously, it is a 4. And I'm actually really surprised that ASUS decided to, go for a 4-phase. And I had a very long discussion about this design decision from ASUS with Elmore, who used to work at ASUS until, a couple days ago. So, what is going on with this VRM? Well, this block right here is, of course, vCore, and then this block over here is iGPU power, so we're just going to call that vGPU. And the vCore portion looks like a 1, 2, 3, 4, 5, 6, 7, 8 phase, except for the part where this voltage controller is an ASP 1400, and the ASP 1400 doesn't do 8 phases. It does 4 plus 2, I think. I'm not entirely sure about if it's plus 2 or plus 1, but it's probably plus 2 because that's really not that's not an exactly rare configuration for a budget voltage controller. This really isn't. The ASUS high-end part is the ASP 1405, and this is the 1400. So this is the cheaper voltage controller that ASUS uses for all of their cheaper motherboards. So we already have some cost savings here. And vGPU is therefore probably a 2-phase. Now, the vCore VRM doesn't use any doublers, so you do end up with a VRM that is basically groups of two like this, and that means it's 4 phases. And ASUS, in their defense, released these lovely scope shots, which show that the new 4-phase has much better transient response than the old extended 8-phase, and by extended they mean that this had doublers. And so let's just write out what these different VRMs were. So the old one was an ASP 1405. All right, so the nice expensive voltage controller that's probably from International Rectifier, going into an IR 3599. That's how we know it's probably from International Rectifier. And that IR 3599 was going into an IR 3535. It's how we further confirmed that it was probably, this is probably an IR chip. So that's a 3535. And that would finally output to a ZF 906 MOSFET from Vishay, dual NFET from Vishay Semiconductor. And that would finally and that would switch current into the 400 nanohenry inductors that ASUS likes to use. And these are important here because when you put your inductors in parallel, stuff happens to them. And here they're not in parallel because we do have the doubler. So that's the old design. The new design is a case of ASP 1400 into 2 639s, and those then output into 2 400 nanohenry inductors. And the thing about this setup is that, well, by having the inductors in parallel like this, and that then goes off to vCore. So this is like the 1 phase of the new design, and this is 1 phase of the old design. And the thing about this new phase with the 2 400 nanohenry inductors in parallel is that effectively you can just ignore that and say they're 200 nanohenries. So their inductance gets effectively cut in half. There is a little bit of an issue that there's the RDS on of the MOSFET in the way from them being completely in parallel, but you can more or less ignore that because the RDS on is so very low. So you effectively end up with an inductance of 200 nanohenries. And the thing about having a lower inductance is that the higher the inductance of your inductor is, the more it resists changes in current. And transient response is all about not blocking changes in current, right? It's about your ability to go from 45 amps output to 193 amps output as quickly as possible. So less inductance means better transient response. So that is already an advantage in favor of this 4-phase design in this test that ASUS has released, right? This, mind you, is not a CPU running at 45 amps and then 193 amps. This is a synthetic load, which is why this looks so very clean, because normally if you have a CPU running, this is going to be a horrendous mess. But anyway, so, you go from that 45 amps output to 193 amps output, and, having a lower output inductance on your phases helps with that transition quite significantly. So already, this 8-phase is losing the battle, like, as far as being designed for maxing out your transient response, well, this should go. Like, that should just be replaced with 200 nanohenry inductors instead. And that would improve the transient response here a little bit as well. Now, the other thing that ASUS points out, like ASUS says they're getting rid of the doublers because doublers introduce some delay to your PWM signal. So the ASP1405, when the ASP1405 sees that you've gone from 45 amps output to suddenly a lot more, 193 amps output, it basically goes and tells pulls up the PWM lines and tells all of the phases to try turn on as quickly as possible. And the 3599 is in the way of doing that because the signal to pull the phases high has to go through the 3599, which delays it a little bit because there's some logic in the 3599, and then it goes to the 35, and then to the ZF906. Now, this is another, and so ASUS is like, okay, we eliminated the 3599, and therefore we've eliminated the delay introduced by the doubler, which is why we're getting this huge improvement in transient response. But do keep in mind, not the same inductors. And the other thing worth noting is the ZF906 is really slow. Like, really freaking slow. This chip, in its own data sheet, for 10 volts gate to source, so way more drive voltage than ASUS ever uses. And like, I talked to Elmore about this. Apparently they drive everything with 5 volts. But anyway, with 10 volts gate to source, and 1 ohm of RG, so resistance on the gate, which incidentally is the typical resistance of the gate of this MOSFET, just normally, that's just kind of how much resistance it has. This thing takes 35 nanoseconds to turn on. The 3599 adds about 15 nanoseconds to 10 to 20 nanoseconds of delay to a signal, depending on what kind of signal you're talking about. Like, more than half the delay in this system is from the MOSFET. I mean, I'm sorry, but what? Like, if this spike is caused by a 50 nanosecond delay, like this undershoot is caused by a 50 nanosecond delay, total, then you could probably get rid of a good chunk of that delay by just changing that MOSFET. Or even better, get rid of the driver and the MOSFET, replace it with an integrated, use the same SiC S639 power stage. That would be the fairest comparison. Basically, what you can see in these scope shots, what I'm getting at here is that the old scope shot is showing a VRM design that really isn't optimized to get the best transient response, right? It really isn't, like, that doesn't seem to have been the main concern of anybody when they were building this VRM. Because if it was, they could have done a lot of things to get better transient response without having to get rid of that doubler. Like, there's a lot of things they could have done. They could have reduced the output inductance. They could have actually, you could keep reducing that output inductance. The reason why you use a higher inductance inductor is that it improves your output ripple. But if you're using a doubler, and then, if you just if you get a ton of phases, right, crank up your switching frequency, then you can use really low inductance inductors, and it doesn't doesn't cause as much of a problem because you have a lot of phases interleaving, and that inherently reduces your output ripple without relying on a huge amount of inductance. But well, ASUS decided, like, ASUS has a ton of these 400 nanohenry inductors, and they just kind of use them everywhere. So, yeah, I kind of like that. That I'd consider probably a cost-saving measure as well. But basically, this is not a fair comparison. This VRM design has, you know, it's like the 3599 puts some delay. Definitely, it definitely adds some delay. But so does the driver, so does the MOSFET you're using. Like, the delays caused by this combination right here are different than, you know, what these have. And it favors these just because integrated, like, the great thing about power stages is that they can turn on much, much faster because the silicon turning on your high side MOSFET is on the same die as the high side MOSFET. So you can get rid of a lot of the parasitics that are in the way of turning on a high side MOSFET really, really quickly. Like the wire that you're connecting to the gate of the high side MOSFET, that, you know, makes it harder to drive it. The inductance of that wire makes it harder to drive it. Like, just power stages have huge advantages when it comes to being able to turn them on and off really, really quickly. So the old design is just like, you could get rid of the 3599 in there and it would probably still, like, it would almost certainly still lose on a transient load response test just because of how it's built. So not a fair comparison. Though it is worth noting the new design definitely has better transient response. And because the ZF906 is so bloody slow, this new design actually manages to maintain the same VRM efficiency at 500 kilohertz, whereas this one, if you run it at 300 kilohertz, is actually worse efficiency at 200 amps output than the new one. So, like, I can see why the 3599 was in the old design. It was there to, you know, get good enough efficiency out of the ZF906s. Because these aren't great. But the new design, you know, comparing it against the old design just isn't really fair to the old design, because the old design was evidently never built with considerations of, like, running a 9900K, and just worse in every way possible, really. The only real advantage is that, you know, it should have a lot less input ripple because it does have the higher inductance inductors and higher and more phases. But, you know, they'd also be running it at a lower switching frequency to keep the power loss in the ZF906s down. And so ultimately your input and output ripple might actually end up being the same on the old design compared to the new design, just because these suck. Well, they're just not really what I would like. The thing is, I would just not use this MOSFET for a motherboard application. Like, the high side is really, really slow and really, really low RDS on, which is, like, great, except for the part where, like, your primary goal with the high side MOSFET is to make it fast, right? Like, it's all about speed. The faster it can turn on, the less power loss you get, especially at lower output voltages. So admittedly, like, yeah, just very different priorities, essentially, between the old design and the new design. And the new design, you know, prioritizes transient response and prioritizes cost savings, because the funny thing is, this is cheaper than that, and 3599s cost $0.46, and ASUS has stopped using 3599s on the entire Maximus XI lineup of motherboards. There's not a single motherboard that I'm aware of from ASUS that uses 3599s, which means, and also with the RTX 2020 series of GPU, there's no doublers on those either. So ASUS can basically stop buying 3599s going forward, and that's a huge cost saving, right? Like, massive cost saving. So it's basically a case of, like, oh yeah, we're saving a bunch of money, and it just so happens that our new VRM design is better at transient response than the old design, which really doesn't seem to have been designed for that in the first place. It's like, whoa, what an achievement. You've saved money and improved transient response. Great. That still doesn't change the fact that it's a 4-phase and that it does have all of the downsides of a 4-phase compared to an 8-phase. Like, for example, the fact that when one of these phases turns on, you get a 50 amps, like, because let's say this VRM is pushing 200 amps output, right, combined across all of these phases. If it's pushing out 200 amps, one of these phases turns on, that is a 50 amp spike that the input filtering componentry has to deal with. Like, Whereas if they were still using doublers, that spike would be 25 amps because instead of, having one 50 amp block turning on, you'd have 25 amps separately. So this would turn on, that would be a little 25 amp spike, and then the next phase would turn on, and that would be its own little 25 amp spike, and that puts a lot less strain on your input filtering circuit, input filtering system than a 4-phase. Similarly, on the output, you would have less output ripple if you just had more phases. And overall, it's just a case of this is a 4-phase. Now, it is still relatively efficient. It's really not that bad in efficiency, but that's mostly down to the SiC 639s just being freaking amazing compared to, these. So, that kind of seems to be the logic that ASUS went with, is our new power stages are so much better than what we were using before that we cannot use the doublers. We'll still get perfectly good efficiency. Our input ripple will go up, but we can deal with that with just better input filtering componentry. Or arguably the input filtering was overkill for the old design, and so they didn't need to redesign that because this sure looks like what they've been running for every motherboard for a while. I don't think they've changed anything about the input filtering setup. Save some money, transient response improves, input ripple gets worse, output ripple you can compensate for with switching frequency as well as with output capacitors. You can just try redesign the output filtering and that could fix that as well, which is rather that's easier to do than, fixing something like your transient response with capacitors. That's actually quite hard. But, yeah, it's still a 4-phase. And, and with it comes and it does at least take, they do still get some advantages that an 8-phase would have. Because this has, 8 power stages in it, it does spread the workload over 8 power stages, but it's not balanced. So essentially, they're normally what you would do when doing this kind of setup is you'd bin your power stages so that they most equally match each other in terms of on resistance, because there's going to be some manufacturing variance between them. And if you put one power stage that's a lot lower resistance than another one, then, you'd have problems. Well, you'd have one pushing more current than the other. But basically, you have less than ideal efficiency with this, less than ideal ripple situation. But you still get the benefit of okay, so we spread the heat output across more or less 8 components. Not quite perfectly evenly, but pretty much evenly. There's not going to be that much variance between them. There will be some, but not, extreme amounts. And so you have something that's a 4-phase. It's a massive 4-phase. That's the best way to describe it, because each of these SiC 639s is a 50 amp DR MOS. So you effectively have a 100 amp peak output capability phase, and you have 4 of them, which is that's just kind of silly, but sure. You can do that. There's nothing really stopping you from doing that. It's just, it's just not an 8. It's not an 8-phase. So the end result here is that in terms of VRM efficiency, this VRM also doesn't win any awards because, well, the new power stages are great, but there's not quite there's other board vendors with just more phases, and more phases generally means easier time dissipating the heat, easier time getting higher efficiency, right? Admittedly, ASUS could have probably put 3 power stages next to each other. There's really nothing stopping them. I actually said, why don't you just put 3 of them next to each other? And they're yeah, we could. We just don't feel like doing that. And it's just, well, I guess eventually ASUS will do that as well. At that point, I really hope they bump up the inductance of their inductors, because at that point, it'd be cut in 1/3. And at that point, they might start having an output ripple problem. Though they might also go oh yeah, but our transient response has gotten even better, so screw it. Anyway, output efficiencies. So 500 kilohertz switching frequency, which is a huge advantage over the old design. The old design would have been 300 kilohertz. 300 kilohertz max. Because if you went much past that, it would get really inefficient. And if you wanted to run it more efficiently, you could have gone down to 250. But anyway, 500 kilohertz here, 5 volts drive. DRV, and 150 amp, and then for, like the data sheet for the SIC 639s is spec'd in 1 volt output, and I've scaled it up based off efficiency to 1.3 volts output, which is kind of worst case scenario scaling, because generally power stages get a bit better with higher output voltage, but it really depends on how they're designed. So, like you could, in theory, it would be possible to design them that they have peak efficiency at 1 volt output and it just gets worse from there. So, anyway, 150 amps output. This VRM would produce about 13 watts of heat at 1 volt and about 17 watts of heat at 1.3 volts. For 200 amps output, you'd be looking at about 20 watts of heat and 26 watts at 1.3 volts, possibly less. 250 amps output, and also this is like 9700K, 8086K, 8700K completely maxed out. This is 9900K, pretty much maxing out any kind of cooling system. So 250 amps output, you'd be looking at 30 watts at 1 volt and about 39 watts at 1.3 volts. And then 300 amps output, you'd be looking at about 40 watts at 1 volt and 51 watts at 1.3 volts. And 400, well, it doesn't go up to 400, it goes up to 360 amps, because while these are 50 amp power stages, they do only, the data sheet ends at 45 amps output, which is pretty normal for most high-end power stages. Is just like, practically speaking, pushing the rated current through a power stage is not practical. So that's something to keep in mind. And the end result is that I can only go up to like 360 amps here. It's 360 amps output, 1 volt, 63 watts, and 1.3 volts, you'd probably be looking at around 82. So yeah, this definitely doesn't win any VRM, awards for VRM efficiency. If they put more power stages in it, they could have improved the figures a bit. They wouldn't even need to increase the phase count, but I guess they'd start running they'd have to relay out the board a bit to accommodate all the extra power stages. And the other option they could have gone for is like a 5+2 phase controller, but at that point they'd have to upgrade the controller to something more expensive, and yeah, they're not going to do that. If they're saving money by getting rid of 3599s, yeah, I don't think they're going to be upgrading the voltage controller. So yeah, I mean, it's not winning any awards for efficiency. It's not terrible either, right? Like, this falls pretty much in line with the ASRock Taichi Ultimate board. It is just worth noting that the Taichi Ultimate probably has a better heatsink than this. And also has, I'm not sure if it actually has more surface area, but like, it really, like, if you have the same heat output as your competitor, then you better hope you have a better heatsink, because if they have a better heatsink, they're winning. So that's one thing to keep in mind. And yeah, it's just efficiency-wise, it's not incredible. The other thing is, with these efficiency figures, I am assuming completely even load spreading across the power stages, which that would, like, imbalanced loading of the power stages would maybe decrease the power efficiency by a couple percentage points as well. So that's another thing to consider, is just like, there's no current balancing on this thing, other than like, hopefully they matched up the power stages pretty well, or that there wasn't too much manufacturing variance between the power stages. So yeah, it's a 4-phase. It's not the most efficient thing ever. It does get really great transient response, but they could have probably just done better on the old design anyway. I'm not impressed, and especially at like $300 that ASUS charges for this motherboard, it's just, like, I know for a fact there are other boards that have more efficient VRMs. I know for a fact there are a bunch of boards with more phases than this VRM. Like, way more phases. Like, some of them have like 3 times as many phases that are like out of phase with each other because they use doublers. And aren't trying to save money on, low-cost voltage controllers and getting rid of chips that cost less than $50. Though admittedly, once you spread that over the fact that ASUS is dropping the doublers off of their entire lineup, it starts making sense that, you know, that's a pretty significant cost saving. And basically, like, ultimately, I think the ASUS claims to the great transient response, like, you'd really have to test this in the real world. Like, you'd have to take this motherboard and compare it against a bunch of other motherboards with, like, the same CPU and try work all of the motherboards down to, like you'd have to have an oscilloscope hooked up to it at the same time and just, like, compare the output on every single one of the boards and just see which motherboard ultimately, you know, can run run the chip at the lowest voltage. And I honestly I'm not sure that you would see a huge difference. The one thing I've noticed throughout testing a lot of motherboards is once you once you get a 4-phase and then go past, like, admittedly that was with like 7700Ks and like 8700Ks. Once you had 4 phases, you kind of were good enough for quite a lot of the higher current outputs. But then the 9900K pulls more current than anything before it. So, you know, it might turn out that this design decision by ASUS in the real world is actually a fail. Like, somebody would have to actually test it and just see, like, which of the existing motherboards can go down to the lowest voltage. I have a hard time, like, I don't think this big improvement in transient response in the real world will actually translate to quite the advantage that these scope shots make it look like it would. So also it's like, also the other thing is you have to consider that everybody, like, no, as far as I'm aware, I don't think anybody has a VRM that looks quite like, as far as I'm aware, a lot of the, like, the other Z390 boards don't have a VRM that looks like this. So yeah, I mean, I can, like, it's mostly a cost saving thing. It's a cost saving thing because they save on the 3599s. The transient response, you know, they've improved that, but I mean, there was ways to improve that without getting rid of the bloody doublers. So it's just like, I don't know. You know, you'd need to test this in the real world. Efficiency wise, it's not exactly groundbreaking, and at the same time, you know, ASUS has some of the more aesthetic-oriented heatsinks out there. So, yeah, you know, testing needed. And actually, for VRM thermals, we already know for a fact that this is one of the hottest running motherboards in the $300 price category. And I'm not surprised. Like, this is, like, because the thing is, like, even within the same efficiency, they just have the heat spread across less components. And that already hurts your VRM thermals. So yeah, I'm not impressed. I'm really not impressed with what ASUS has done here. Then again, ASUS rarely manages to impress me with their VRMs most of the time, because most of the time ASUS has an approach to VRM design that's very much a case of good enough, right? Like, they've had the same 8-phase VRM on their high-end desktop motherboards since X79. And I'd argue that for X299, it's really not good enough. But hey, that doesn't stop ASUS from reusing it over and over and over and over and over again. And I also don't think it's good enough for X399 either, but they used it there as well. So, yeah. That's kind of that. Anyway, let's cover some of the other stuff on this board, since we do have just about enough time to do that. So VCCIO, VCCSA are located down here. You have a clear CMOS and flashback on the rear I/O, BIOS flashback on the rear I/O there. The extra 4-pin power connector is optional. Your 9900K is going to be uncoolable before you max out your single 8-pin. Unless you delid and, like, run liquid metal, maybe sand down the die, you really will probably, you know, max out your cooling system before you max out the 8-pin power connector. You have a postcode up here. You have some troubleshooting LEDs below that. These are color-coded, which I really, really like, because a lot of other board vendors, what they'll do is they'll put them in the same color, and then one of them lights up, and it's like, well, I don't know which LED it is, because they occupy 3, you know, like half a centimeter of space on the motherboard, so it's really hard to tell which of the 4 LEDs lit up if it's not one of the ones on the edges. And they're all the same color. And when they're glowing, you know, you look at it and it's just like, well, I can't see anything. The LED lit up and it's blinding me. So it's nice that ASUS color codes these, because that makes it much easier to figure out which one's going off. You have a power button, reset switch, 2-phase VRM for memory power. This is a standard ASUS memory VRM. They've been using it for years as well. Controlled by ASUS favorite ASP, well, that's another one of those rebrands, but ASP 1103. We've been seeing this chip for ages and ages and ages from ASUS. Going down the board, we also have a retry button down here and a memo K switch. I don't understand what this is supposed to achieve. Apparently, it allows the board, like it disables and enables the motherboard's ability to retrain, which seems really stupid because motherboards tend to get stuck in like boot loops when you let them retrain forever. I would have much preferred if they had kept like if this either had a safe boot button or the old memo K button. The old memo K button, what it would do is if you would get bad memory settings, you'd hit the memo K button and it would load up. It would basically wipe your memory settings and load up some really nice safe presets. Whereas this seems to just be kind of like train until it works and hope for the best, which generally tends to be a terrible idea because boards tend to not like. A lot of boards, when they get stuck on training, they're stuck on training. They don't tend to ever figure out what's wrong. So not a huge fan of that, especially because the retry button gives you the retraining capability anyway. Like you can just use that. And also that's like a hard reset button. So yeah, board doesn't have dual BIOS because, ASUS doesn't do dual BIOS for a lot of their cheaper boards, which this isn't even cheaper. But the thing is, ASUS really considers, like, for Intel motherboards, the Z39, like, Intel motherboards from ASUS, $300 price tag, that ASUS considers that mid-range, which is why they expect you to use this with, like, a 9700K. And the VRM kind of reflects that as far as I'm concerned, because at least at 150 amps output, it really, like, it's producing very little heat whatsoever. So, yeah, that is the Maximus XI Hero. It is a 4-phase. It's 4+2. And ASUS might want to call it a twin 8-phase, but the fact of the matter is, those phases aren't out of, like, there's only 4 signals out of phase with each other. I don't know what other things could be out of phase here, but there's only 4 of them, That's kind of the point of having phases, that they're out of phase. If you're going to be shoving one PWM signal into 2 power stages, they're not going to be out of phase with each other. You can't call them separate phases. That's like if 3-phase power was made with one sine wave on 3 different wires, and that sine wave was in phase with each other. Like, that's basically what they're saying. Like, no, it doesn't work like that. So, yeah, that is it for the video. For $300, I really think this is, I guess you get the ASUS tax for ASUS BIOS, I guess. Because that's one of the things where ASUS still absolutely dominates, is probably the BIOS. But you can learn a gigabyte BIOS. You can't fix the VRM, right? Like, you're not going to be you're not going to be replacing the VRM on a board. You can also, you can tolerate ASRock BIOS as far as I'm concerned. Like, I don't have a problem learning it. It's just janky as hell to use as far as I'm concerned. So, yeah, that is it. Thank you for watching. Like, share, subscribe. If you have any comments, questions, suggestions, you can leave them down in the comment section below. If you'd like to support Gamers Nexus, we do have a Patreon, as well as store.gamersnexus.net, where you can pick up things like shirts, as well as the mod mat that you can see in the background of the photo here. And, yeah. And I have a channel called Actually Hardcore Overclocking, if you'd, where I do more overclocking related content, so if you'd like to check that out, that would be awesome. Thank you for watching, and goodbye.